All right, so as a physio student, you've probably seen your fair share of tendinopathy, right? You know what it looks like, what it feels like for the patient. But have you ever wondered what's really happening way down at the microscopic level? Like, what does it actually mean for a tendon to fail? Today, we're going to connect that deep mechanical engineering stuff, the micro-level strain, to the real-world pain you'll be treating every single day in the clinic.
Okay, so here's our game plan. First, we're going to build up the classic, perfect textbook model of a tendon. Then we'll look at how real-world data just completely blows that model apart. From there, we'll introduce a newer, much better model that actually fits what we see. And the whole time, we're going to be asking, what does this mean for our patients? How do we get from strain to pain?
All right, first up, modeling the unseen. Look, a tendon is insanely complex, right? So to even begin to understand how it breaks down, we've got to simplify things. We need a model, a framework, that lets us get a handle on what's going on.
And that main tool is something called continuum mechanics. Now, that sounds complicated, but the idea is actually pretty simple. Think about it. A tendon is made of zillions of tiny little particles and fibrils. Instead of trying to track every single one, which would be impossible, we just zoom out. We treat the whole tendon as one single continuous thing. This is a huge simplification, but it's super powerful. It lets us apply the laws of physics to predict how the whole structure will behave under force. It's the foundation for understanding stress and strain.
Okay, so now that we've got our basic tool set, let's look at the classic picture. This is the ideal textbook story of how a perfect tendon is supposed to act when you pull on it.
So if you were to graph the stress versus the strain on one of these ideal tendons, you get this really neat, classic curve. It all starts in what's called the toe region. Basically, you're just taking up the slack, kind of straightening out the natural waviness of the collagen fibers. Then you hit the linear region. This is where it acts like a perfect spring. It stretches predictably. But if you keep pulling, you get into trouble. That's the post-yield region, where tiny little fibrils start to give way and fail. And if you go too far, boom, region 4, complete failure. The whole thing ruptures. This nice clean story was the basis for all the early thinking on this.
So the very first model built to explain that nice curve was called the elastic rupture model, or ER, and it was super simple. It basically said, imagine all the collagen fibrils in a tendon are identical twins. They all stretch perfectly elastically, right up until they hit one single breaking point. And at that exact moment, snap, they all break at once. Think of a bundle of identical guitar strings all snapping at the exact same time. It's a really neat theory, right? But reality is just a whole lot messier.
And here's where our neat little story starts to fall apart. This is where reality bites back. Because when researchers actually hooked up real tendons to machines and started pulling on them, the data they got, well, it just didn't fit that clean, simple model at all.
Yeah, it turns out real tendons just don't play by the textbook rules. They were doing things in experiments that completely stumped that simple elastic rupture model. The data was screaming that there was a massive piece of the puzzle, just missing. Okay, so there were two huge mysteries that the old ER model just could not explain. First, some tendons showed these weird second linear regions. Instead of a nice sharp peak before they failed, the stress would just kind of plateau. It would level off for a while. And the second thing was step-like failure. Instead of one clean break, the tendon would fail in a series of little steps, almost like a zipper coming undone. The old model was completely silent on both of these. It had no answers. And you might be thinking, okay, maybe this is just a rare exception. But no, not at all. A big analysis looked at the data and found that a whopping 47% of experimental tests showed these weird features. Think about that. That's almost half. So nearly half the time, the model everyone was using was just fundamentally wrong. There was a giant hole in our understanding. So to solve this mystery, science needed a new detective on the case. We needed a smarter, more sophisticated model. One that could actually account for all the weird, messy things we were seeing in real life. And that new detective is the Elastic Plastic Distribution Model, or EPD for short. The name itself kind of gives away the secret sauce. It has two huge upgrades that let it finally solve the case.
Okay, so here's the fundamental difference. The old ER model, remember, assumed every single fibril was a perfect clone. They all break at the same time. The new EPG model says, no way. A tendon is more like a diverse population. You've got strong fibrils, you've got weaker ones. They don't all fail at once. Their breaking points are spread out across a distribution. That's the D in EPD. And the second big idea is plasticity. This means that before a fibril snaps completely, it can deform permanently. It can get stretched out and not quite bounce all the way back. It's like accumulating damage. The old model didn't account for that at all.
And the researchers themselves put it perfectly. They said, the key difference is the use of distributions to describe the fibril yield stretch and rupture stretch. And that right there is everything. That shift in thinking, away from one single breaking point to a whole range of breaking points. That's what finally cracked the case.
And once you embrace that idea of distribution and plasticity, those old mysteries just vanish. That stress plateau? Well, that's explained by the time lag between when fibrils start to permanently deform, the yielding, and when they actually start to rupture. And that step-like failure? That's what happens when you have a few different groups of fibrils within the tendon, and each group has its own average breaking point. So one group fails, then the next, pop, pop, pop. It all makes sense now.
And the numbers back this up, big time. You're looking at a measure of error here. Basically, how far off the model's predictions are from reality. The old ER model had an average error of about 4.5. The new EPD model, just 2.29. It slashed the error by almost half. This isn't just a minor tweak. It's a fundamentally better description of what's actually happening inside a tendon.
Okay, fantastic. We've solved the mechanical puzzle. But so what? Why does any of this matter to you and the patient in front of you with a painful Achilles tendon? Well, this is the most important part. This is where we build the bridge from the engineering lab straight into your clinic. In the clinical world, this all connects beautifully to something you've probably heard of, the tendinopathy continuum. This is a framework that helps us see tendon injury not as a simple, is it torn or not question. Instead, it shows us that tendon health exists on a spectrum, and an injury is a process that unfolds in stages. And this continuum generally has 3 stages. First, you have reactive tendinopathy. This is often a response to a sudden overload, like a weekend warrior who overdoes it. The tendon gets angry, it swells up, but the structure is mostly intact. It's a warning shot. If that overload continues, it can progress to tendon disrepair. Now we're talking about the structure starting to break down. Things get disorganized. And finally, you can end up with degenerative tendinopathy. Here, the changes are pretty much permanent. The tendon tissue is weaker, less able to handle load, and much more likely to rupture.
And this, right here, is the million-dollar connection. This is the big so what. That mechanical failure at the micro level, the individual fibrils yielding and rupturing that our EPD model describes so well, that is what drives the biological response you see at the clinical level. That tiny damage is the spark that lights the fire of tendinopathy.
So this really matters because a better mechanical model gives us better clinical reasoning. When we understand how the fibrils are failing on a microscopic level, we can finally understand why our patients are in pain. And more importantly, it guides our treatment. It's why for a reactive tendinopathy, the answer is often to calm things down and reduce the load. But for a degenerative tendon, the right kind of specific, controlled load is exactly what it needs to get stronger.
And this really opens up the next big question, doesn't it? If we can model failure this accurately, what's next? Could we design truly personalized rehab programs based on an individual's tendon mechanics? Could we even predict who's at risk of injury and intervene before they ever feel that first twinge of pain? That's the frontier. That's where all of this is heading. And it's amazing to think that it all starts with understanding exactly how one tiny microscopic fibril finally gives way.